Okay, let's get started for this week's tutorial, and we will be starting with exercise 1.4, and later on we will be covering 1.5 and 1.6 in this session. So this exercise 1.4, it's about predicates and quantifiers, and it can be found on page number 156 of your textbook. Okay, so I am not sure if you guys are able to hear me. Can someone gives me a quick reply that you guys are able to hear me out?
Yeah, we can hear you.
Okay, okay, let's get started now. So, um, starting with the question number 2 of this exercise 1.4. So we have this P of X, which represents the word X contains the letter A. And based on this, we have to determine the truth values for P of orange. For the part A, we would say that this is true. The truth value for this statement will be true because there is an A in orange. So therefore, this statement will be true. For B, we would say that this is false, and for obvious reason, because there is no A in lemon. Uh, Part C, we would say that this is also false for the same reason, because there is no A in true. And part number D, likewise, this is true because there is an A in false. Okay, this was a pretty straightforward question. So if you guys have any question. All right, seems like everyone is clear on this part. Let's move on to the next one. Okay, so in this exercise, in this question, we will have to translate these statements, the proposition statements, and then there are some quantifiers with it. So this sort of an upwards down A represents for all, and then the E here, the other E here represents there exist. So we will have to translate these into English statements. So this R of X represents the statement is X is a rabbit, and H of X represents X hops, and the domain consists of all animals. Okay, so based on the information that we are given, we will, for part A, we will say that so we have this for all quantifier, and then we have R of X, and then there is this conditional, and then we have the X of H of X. So we can say if an animal is a rabbit, then that animal hops. Okay. Or we can say every rabbit hops. Okay. So in this first part here, we are representing the relation of this conditional with the if then, which is perfectly fine and very clear in this statement. And then we have this for all quantifier, which we are saying if an animal. So because this is an animal, is the animals are our domain. So we are saying that if there is an animal that is a rabbit, then that animal hops. Part B. So we have this for all x, we have this r of x, and then this here sign is of represents and this h of x. We will say every animal is a rabbit and hops. So we use the word every for this for all x, every animal. This r of x represents x as a rabbit. So every animal is a rabbit. And then we use this and to put the word and then we have this h of x, which represents hops. Part C. Okay, so part C, there is this, there exists x. So this as quantifier here represents there exists an x. So here we will say there exists an animal such that if, because we have this condition, so we will be using terms like if then. So there exists an animal such that if it is a rabbit, then it hops. Lastly, part D, we have the same existential quantifier. We have the and then we have r of x and h of x. We will be saying there exists an animal that is a rabbit and hops. Or we can say some rabbit hops. Or just to give you another idea, we can also say or some hopping animals are rabbit. Okay, so there are different ways of saying the same thing. So we are just expressing these propositional statements by using the English language.
Sure. Is it possible to post this recording like for future use? Because I didn't get to these questions yet.
Are you asking for if the video is recorded?
Yeah.
Yeah, the video is being recorded. Yes, it is being recorded. Yep.
Uh, you know where it will be posted?
Um, I am not quite sure where it is posted, but I think is your course on e-class?
Uh,
Is it on Moodle, e-class, or
It's on Microsoft Team.
yes? Okay, then you can find the recordings there. You can ask the professor but I will be asking him this question as well. So by the next tutorial, I will have an answer for this question as well.
Okay, thank you.
Yep. Okay. Any questions for this part?
Yeah, I have a question about C.
Yep.
Does that logically mean that only rabbits can hop and other animals cannot?
So we are saying that there is there is an animal, but we are not sure if it is a rabbit or not. But we are saying that if it is a rabbit, then it hops. These part B and C, they wouldn't make much sense in like when we're using it in English language, because we cannot say that every animal is a rabbit, right? Or we cannot say that there is an animal such that if it is a rabbit, then it hops.
Yeah, so now what's the difference between C and D? Because I can't understand the difference between them.
C and D.
C and D.
Yeah. So in C part here, we are not saying that yeah, so we are basically assuming that this R of X, which is X is a rabbit, we are assuming that if this is a rabbit, then it hops. But
Mhm.
in the part D, what we are saying is we are saying that there exists an animal. We are saying that there is an animal that is a rabbit. We know that there is an animal that is a rabbit. In part C, we don't know if we have an animal that is a rabbit or not. But we are assuming that if an animal is a rabbit, then it hops.
Okay, I got it. Thank you.
Any other question? All right. If not, let's move on to question number 14. In here, we have to determine the truth value of each of these statements if the domain consists of all real numbers. So in determining the truth value, we see that knowing the domain is very important because our answers will be based on the domain. Now that we know that our domain consists of all real numbers, so we can answer more precisely. So for part number A, we have there exists an x such that x cubed equals to -1, right? We know that there is an x for which we take the cube of it, it equals to -1. So for example, if I take the -1 cube, so this equals to -1, right? So therefore we can say that this is true. For part number B, we will this statement translates to there exists an x such that x to the power of 4 is less than x to the power of x to the square. Okay, so here, for example, we can take any x in the domain we have, and the domain is real numbers. So for example, we can take fractions too. So if we take a fraction, let's say if I take the number 1.5 or 0.5, so I will say here, for example, 0.5 represented by 1/2. If I take the fourth square 4 of it, the power 4 for 1 as divided by 2, then we know that this is going to be less because this is equals to 1/16, I guess. And we know that this will be less than 1/2 to the power square, which is equals to, I guess I'll just put here comma and then I'll say 1 over 4. 1 over 4. Now we know that this value here, 1 over 16, 1 over 16 is less than 1 over 4. So therefore we can say that the truth value for this is true.
I have a question.
Yep.
So what if I choose like a value of 2?
A
If
value,
I choose, yeah, a value of 2, then this will be a false statement.
yeah, so for example, if we take a value 1, 2, 3, 4, any value that is not a, maybe that is not a fraction.
Okay.
Yeah, so for example, if we take the value 2, this is going to be false. But because this quantifier here tells us that there exists a number in the domain of real number.
Oh, right. Okay. Got it. I understand it now.
Yep. All right, let's move on to part number C. So we have for all x, we have minus x squared equals to x squared. So we know that whenever we take a square, the power square of any number, either it's positive or negative, it turns out to be a positive number, and it is equals to like the positive square of itself. So for every number, we have this minus x to the power of 2 equals to x to the power of 2. Therefore, truth value is true. Should I say for every real number? Just to also quote the domain. Part D. So we have this for all x, 2 of x, 2 times the same number, it's going to be greater than the number itself. So we can say twice a positive number is larger than the number we know that, but there are some cases, for example, but this inequality is not true for negative numbers or even 0. Therefore, it's false. So for example, if we take x as 0, then we say 0 is greater than 0 is logically wrong, because 0 is not greater than 0. 0 is equals to 0. So therefore, the truth value of this proposition statement is false. Questions? All right, let's move on to question number 30. Okay, so here we are supposing the domain of the propositional function. So this here is a proposition function, consists of pairs x and y. So where x is 1, 2, or 3 and y is 1, 2. or 3. Write out these propositions using disjunctions and conjunctions. So this symbol here represents disjunction and this represents conjunction here. So let's take part A. We have there exists X such that P, X, and 3. So we have to uh, basically write out the proposition using disjunction and conjunction. For example, we can say there exists an X. So we can say, we can take X as 1, right? So this will be 1, 3, or it can be P. We can take X as 2 because X can be 2, 1, or 3, right? So we can take this, or we can say X can be 3, 3. Part B, for all Y P1Y. So here we have to decide upon the value of Y, and we already know Y can be 1, 2, or 3. So we will say P P11, and here we will be using the conjunction because of this for all operator. So when it's for all operator, we have to use conjunction because we are here stating a very strict condition. We are saying for all and not we are and not there exist. For there exist, we will be using this disjunction. For all P1, 1, 1, 2, conjunction P 1, 3. Part C. Here in the part C, we have the there exist operator. So we know that we need to use this disjunction, but we also have a negation in front of it. So we need to consider that as well. So we will be saying that negation of P X is 2, right? So we have 2, 1. We have uh, the disjunction operator. We will use the conjunction operator, and the negation operator. We will saying negation of P 2, 2, and then we have the disjunction negation P, and then we will say 2, 3. So 2, 1, 2, 2, 2, 3, disjunction with negation in front of each propositional function. Part D. Part D will be likewise, we have this negation sign, and we have this for all X. So we know that we need to use the conjunction operator. So I'll just copy this and make changes to this. So we have this for all. First, we will need this conjunction instead of the disjunction. And then we say 1, 2, 3, and we have 2, and we have 2. Okay. So we will be basically taking this negation, and then x can be 1, x can be 2, x can be 3, but the y remains 2, right? And then we are using this conjunction because of the for all x. Questions? Right, if no questions, let's move on to exercise 1.5. This can be found on page number 68 of your textbook. Let's do the question number 1. So we have these statements and we need to translate them into English. So where the domain for each variable consists of all real numbers. So we know that the domain we have is basically all real numbers. We will take the first statement, part A. Okay, so we have this for all x, and then there exists y, and then we are saying x is less than y. Here we don't have to determine the truth values for this. We don't have to say which x or y we're taking. We only have to translate them. So this makes the work a little bit easier. We will be saying for every real number, because our domain is real number, for every real number x, there exists a real number y such that x is less than y. So we say for every real number x, represented by for all x quantifier, there exists a real number y represented by their xy existential quantifier. And then we just translate the statements in English such that x is less than y. Pretty straightforward. We take part B. This is a pretty long one, but don't be intimidated by its length. So we will say for every, we just take the quantifiers, put them into English. For every real number x and every real number y, because we have both the for all quantifiers. Now we have to basically put that in this conditional into English. So we know that the most used term for this is if then. We will say if x, and so we are saying x is greater than 0 and y is the greater than 0, or in other words we can say if x and y are both non-negative, right? Then and then we use this part, then their product, because we xy here, product is non-negative. Non-negative basically means positive. A pretty long statement, but very easy in terms of logic. Part C. Here we have three quantifiers. We have x, y, and z. So we say, just like we said before, for every real number x and real number y. Notice that whenever I'm using the word x, y, wherever I'm referencing the uh, these quantifiers, I am also referring the domain. So because it is real numbers, so therefore it's important to also mention the domain. For example, y in real number. So we are mentioning that y is a real number. There exists a real number z such that x, y equals to z, or I can just say or the product of x and y equals to z. Yeah, if anyone have a question, just please go ahead and interrupt me with your question. So some people are asking question in the chat, but while I am um, giving your demonstration, I'm unable to see the chat. So please speak up and ask me your questions. Okay, if no question, let's move on to the next question. So here in this question, we have a proposition function, and then we are given the statement they represent. So q of x, y be the statement x has sent an email message to y, which is represented by q of x, y, where the domain for both x and y consists of all students in your class. Express each of these quantifications in English. So what we have to do is we take this, we convert it into English. Okay, so let's do the first one here, part A. Okay, so we have the domain that is all students in your class. So the domain consists of all students in the class. This QXY here represents that X has sent an email message to Y. Okay, let's do the first one. So there exists, or I can say there is some student, because it won't make sense to say there exists. There is some student in your class, just specifying the domain. Student in your class is the domain, and there is some is coming from this existential quantifier, the first one. There is some student in your class, who has sent a message to some student in your class. Here, this some student is coming from the second existential quantifier, and then we are using this y representation in terms of English. So there is some student in your class who has sent a message to some student in your class. Part C. So part C, we have for all x, and then there exists y, q of x, y, okay? So every student, okay? So every student coming from this for all quantifier, every student in your class, just specifying the domain, we have to be very careful about specifying the domain. Every student in your class has sent a message to, and then we use some student in your class. All right, let's move on to part number E. We have here for all exist y. So notice that we have changed the order of these quantifiers. For all y, there exists an x, q, x, y. Okay, so this one is going to be a little bit opposite. So we will say every student, because of this for all, every student in your class, specifying the domain, very important. Okay, now that because we have switched the order of this quantifier, we will say every student in your class has been sent a message from some student in your class. From some student here, this statement here, to some student in your class, from some student in your class, basically represents there is at least one student in your class who did that. So likewise for the part numbers E, we will say every student in your class has been sent a message from at least one student in your class. So some student basically signifies that there is a student and it is at least one. There can be more, but there is at least one who did that. Questions? All right, so let's move on to the next question.
Sorry, I have a question.
Yep.
Just written it in the chat. So in the last one, if there is if the statement is for all x, for all y, like f, for example, does that mean that there is only one student in X that sent a message to a student in Y, or maybe there are a couple of students in X that sent messages to us to
Yeah.
one
So,
student?
so for the statement F, what we're really saying is it's a very strict condition. What we're
Mhm.
saying here is for the F part is that every student in the class has sent a message to every student in the class. It can either be to the student itself, or it
Mhm.
can either be to the other student.
So it's not strict to be one-to-one function, right?
Yes.
Okay, thank you.
All right. Let's move on to question number 5. Just giving you a minute to read through the question. It's a pretty lengthy one. Okay. So here we have this WXY, which represents that student X has visited website Y. So we have to know the domain. So the domain for X consists of all students in the class, and the domain for Y consists of all websites. So express each of these statements by a simple English sentence. So W, Sarah Smith, and www.att.com. So we already know what this function WXY represents. It takes two variables and then putting it in English word, it means that student X has visited website Y. So we take this Sarah Smith, we know W represents visited website www.att.com. So we can say Sarah Smith has visited website www.att.com. Okay. Okay, part C, this one here. There exists Y. Y is basically consist of all websites. Consist of all websites. So there exists a website. So Jose Oris Y. So we say Jose Oris. Jose, Jose Oris has visited at least one website. Okay, or has visited some website. It can be more than one, but it is not definitely zero. It is, there exists some website which Jose has visited, but we don't know which website, but we know that it is one at least. Let's take a bigger one here, part E, a little bit challenging. We have, there exists a website represented by Y. There exists a website for all Z. For all Z, this is basically uh, for all that, we, because here this quantifier, we don't know what basically it means, because we don't know the domain for that, right? So but what we do know is that it comes in that as I hear in this proposition statement here, so which is represented by the Z part here, which is basically this part in terms of Y, has visited website Y. So if we take just this part, right, just this part, it would mean that David Belcher has visited website Z or Z, right? So, and then if we take this part, it means that Y has visited website Z. Okay. If we put it together, it means if David Belcher visited website Z, then Y visited website Z. And we know that Y is not David Belcher. We know that Y is not David Belcher, and we know that if David Belcher visited website Z, then Y visited website Z. Okay, so in other words, what we are saying there, also taking these quantifiers, so there is a student besides David Belcher, because here we are saying Y is not David Belcher. Besides David Belcher, who has visited this here, who has visited all the websites that David Belcher has visited. This can be a little mind-boggling, but if we just take little pieces at a time, we can construct this statement here, just like I explained to you guys. So we know that if David Belcher visited website Z, then Y visited website Z. But we know that Y is not David Belcher, right? So there is someone other than David Belcher who visited a website, right? And then we are specifying the domain that it is not just one website, it is all the websites. There is someone besides David Belcher who has visited all the websites that David Belcher has visited. Right, let's move on to question number 9. Question number 9, I have already solved it for you guys. So just take a minute to read the question. Okay, all right, so here we have this statement, this proposition function be from L x y be the statement x loves y, where the domain for both x and y consists of all people in the world. Use quantifiers to express each of the statement. So we are given the English statement. Now we have to do the opposite. We have to basically construct the quantifiers to express these statements. So we have to, for part A, we say everybody loves Jerry. So this is straightforward. X loves Y. We know that uh, Jerry, X loves Y. So Y becomes Jerry, right? So we just put Jerry in place of Y, and then we have this X. We have the domain that both X and Y consist of all people in the world. So this statement here, for all X, L, function L, X Jerry represents that everybody loves Jerry. Part number C, there is somebody whom everybody loves, right? So here we have to, we will be breaking it down to into two parts. Firstly is there is somebody. So this will be represented by there exist quantifier, right? There exists. So we have this there exists quantifier. Now we have to decide upon the variable. So whom everybody loves. So this is sort of in an opposite way, right? So we can already decide that it must be variable y. Whom everybody loves. So everybody, we use this for all x, and then we use this quantifier l x y. So there is somebody whom everybody loves. Okay. Lastly, there is somebody whom Lydia does not love. So we have there is X, there is somebody, right? So X is represented by that somebody whom Lydia does not love. So Lydia X, and then we simply put the negation. Okay, right? Let's take a quick break, short break, and then if you guys have any question on this, we can take this. All right, so let's rejoin in few minutes. I'll be remain connected, but if you guys want to grab something, just it's gonna be a quick short break. Okay. All right, so any questions for this question number 9 here? Okay, if no question, let's move on to question number 13. So just take a minute to read the question. Okay, so here we have um, m function m x y, which basically represents that x has sent y an email message, and then we have another function which represents x has telephoned y, and then we are told the domain consists of all students in your class. So we know the domain for x and y is all students in your class. So here we have to use the quantifiers to express these statements, these English statements into quantifiers, quantification statements. So firstly, we have Chow has never sent an email message to Coco. So here X has sent Y an email message. We only need to do that. So X here will be Chow and Y will be Coco. So we just plug in those Chow and Coco in MXY, but we are seeing Chow has never sent an email message. So we just put a negation in front of them like so. So this represents Chow has not has here this statement has sent X has sent Y an email message. So by this negation, we will be saying that Chow has not sent Coco an email message. Part C. Jose has never received an email message from Deborah. We will be doing the same message, just plug in Deborah for X and Jose for Y, and then we will be using the negation for the function M. So Deborah has not sent Jose an email message. Lastly, part E, we have no one in your class has telephoned Nina. So we have another function represented by T. So here TXY represents X has telephoned Y. So we are saying no one in your class has telephoned Nina. Here we need to use the quantification because we have to represent that no one did that. So we will be using the quantification with the for all quantifier. So for all x, x is basically the all students in your class. So all x has telephoned Nina. Everyone has telephoned Nina, and then we will basically put this negation sign to represent that nobody in your class has telephoned Nina. Questions? Right, let's move on to the next one. Here, this question. So question number 21, we have to use the predicates, quantifiers, logical connectives, and the mathematical operators to express the statement that every positive number is the sum of the square of four integers. So because we have four integers, so we have to represent this somehow. So for example, we can take A representing one positive integer, B, C, and D representing likewise some positive integer. And then we have X. So we will be mentioning, for example, A represents, I'll just, A represents some, um, A represents positive integer. So the domain of A is positive integer. Likewise, we can say for B, B, C, and D, domain are positive integers. All right. And then we also have X here, which represents some positive integer as well. So we have defined the domains for these five variables, X, A, B, C, D, which represents some positive integer. Now we have to say that the statement, every positive integer, so we take every positive integer, we take for all X, is the sum of the square of four integers. We said there exists an A, so there is some positive integer A and B, C, D. So there exists A, B, C, D, for which the sum is basically positive. And then we will be showing that if X is greater than 0, we are saying that X, this signifies that this is a positive integer. If X is greater than 0, then X equals to A square plus B square plus C square plus D square. So in other words, we are basically saying that every positive integer is the sum of the squares of four integers. Questions? Right, let's move on to the next one if no questions. Okay, so we have this question number 25, and then we are supposed to translate this into English statement. So we have translate each of these nested quantifications into an English statement that express a mathematical fact, domain in each, just of all real numbers, so we know the domain. We here, let's take part A. Let's take part A, and then here what we are saying that there, so here we are basically here saying mathematical fact. So this x y equals to y is basically represented as a multiplicative identity. So we will say there is a multiplicative identity for the for here the domain is all real numbers, right? For the real numbers, there is a multiplicative identity for all because we are using this all operator. So there is a multiplicative identity for all real numbers. Part C. So we have this, there exist and there exist x and y, which the domain consists of all real numbers. So we are saying that x squared is greater than y and x is less than y. So we say there exists real number x and real number y such that x squared is greater then y and x is less than y. Okay, let's move on to the next one. So what we have to do is we have to rewrite each of these statements so that negation appear only within predicates. So here we have this negation, for example, for question A, we have this negation sign in front of the quantifier. What we have to do is we have to resolve such that the negation only appears within the predicates. That it is so that no negation is outside the quantifier or an expression involving logically connected. Okay, let's take part A. So when we have the negation in front of for all x, and then we take the negation of that, it becomes for there exists x, right? So we converted this for all x into there exists x, and then we converted this for all y into there exists y, and then we simply place this negation in front of this predicate here, the function here. So now that this negation is not in front of the quantifier, but in front of the predicates. Pretty straightforward. Hard one here. So we have now nested quantification here. What we do is we basically take this, uh, because this whole thing is basically quantified over this for all x, and we take the negation, it becomes there exists x, right? And then this negation here is basically negating over this whole thing in the bracket. So now what we do is we basically revert these there exist into for all, and then we basically convert this for all into there exist. We keep those variables, but we will be negating these quantifiers. So here this for all x becomes there exists x, there exists become for all become there exists. Whenever there is this predicate, we just append this negation in front of it. This conjunction becomes this junction because this negation was multiplied or sort of, you know, um, basically, you know, occupying all this predicate. And we just convert this there exists into for all z, and then for all y into there exist y, and then we just put negation in front of it. So a big one, but technically not a very difficult one. Questions? All right, if no questions, let's move on to the next exercise, which is exercise 1.6 on page number 82 of your textbook. So this exercise here is a little different because it involves the uh, the, the logic rules. So we will be studying in this exercise, putting into practice. So firstly, we have the argument form. So this here is given is known as the um, basically the argument form. For the following argument and determine whether it is valid, can we conclude that the conclusion is true if the premises are? So this here statements here, so we have these three statements in 1, 2, 3. So these ones here are called the premises, and then this one here is called the conclusion. We have to determine if this conclusion is true based on these premises or hypothesis given to us. The hypothesis or the premises that we are given is if Socrates is human, then Socrates is mortal. We know that Socrates is human, and then we are concluding that Socrates is mortal. So the rule that we will be using, this rule is known as modus ponens. I hope everyone is aware about this rule. So modus ponens is the rule that we will be applying to it. So modus ponens basically proves that this conclusion is true based on the premises or the hypotheses that are given to us. So modus ponens, we say that this is valid. The conclusion is true. Okay. So we are assuming something. So for example, here we have two hypotheses. For example, any hypothesis. For example, P, so if P then Q, and then we are given hypothesis P. With these hypotheses, we can conclude that Q. So here P represents if Socrates is human, Q represents the Socrates is mortal. P here was basically Socrates is human, right? So this is modus ponens rule. So by modus ponens says that if P then Q, and then we also know that P is true, then Q will be true. So by modus ponens, we determine that this conclusion is logically correct. Questions? All right, no question. Okay. Question 3. So we have to determine the rule of inference for each of these statements. So take part number A. Alice is a mathematics major. Therefore, Alice is either a mathematics major or a computer science major. We have to determine which law it is. I'm sure that you guys have gone through the laws with the professor lectures. So I will be just putting the rule names, and if you have studied the rules, this answer should be straightforward. So the name of the rule of inference is addition, because here we have some information about Alice, that Alice is a mathematics major, and then we are concluding that Alice is either a mathematics major or a computer science major. Okay, so once we have something, so for example, P, addition rules says that we have P, then it is equal to P or Q. So we know that or for this P or Q either evaluates to P or Q, right? So and we say that it is P. So therefore, we know that Alice is a mathematical major. So this conclusion will be correct based on this hypothesis. And even like in terms of English, this is pretty much straightforward to know that this statement is correct. Let's take part C, maybe. Okay. Uh, if it is raining, then the pool will be closed. It is raining, therefore the pool is closed. Yeah. So this rule we just stated. What it says is we have P, and then we have Q, and then we know that P is true, therefore we can conclude Q is true as well. So likewise, we are saying that P represents if it is rainy. So it is raining is represented by P, and then Q represents pool will be closed. We are saying if it is raining and then pool is closed, and then we know that P, it is raining, therefore we can conclude this Q, which basically is the pool is closed. So the rule is modus ponens. Let's do the last one, part E. Part E says if I go swimming then I will stay in the sun too long. If I stay in the sun too long, then I will sunburn. Therefore, if I go swimming, then I will sunburn. Okay. So this rule here basically means if P, then Q, Q, then S maybe, then we can conclude that P, then S. So this rule here, we say P represents, I'll just write the name of the rule, hypothetical, and syllogism. So that's the name of the rule. So it says that if P then Q, if Q then S, this is logically equal to if P then S. So here we will represent P by, let's say P represents I go swimming. I go swimming. Q represents I will stay in the sun too long. I will stay in the sun too long. Let's see if I stay in the sun too long, then it's sunburn. Okay, so we have S, which represents I will sunburn. Okay, so now if we plug in these values in here, we can clearly see that if I go swimming, so if I go swimming, then I will stay in the sun too long. If P, then Q. Okay. If I stay in the sun too long, then I will sunburn. So Q, S. So now we can already see the relationship, right? So this hypotheses are matching here. We can determine that P will basically, if P, then S, right? So P, if I go swimming, then I will sunburn, which is just right here. If I go swimming, then I will sunburn. So therefore, we can conclude this one. Right? So the name of this rule is hypothetical syllogism. Questions? All right, no questions. That's great. Let's move on to the next one. Okay, so what we have to do is we have to basically use the rule of inference to show that the hypothesis Randy works hard. If Randy works hard, then he is a dull boy. And if Randy is a dull boy, then he will not get the job. Imply the conclusion Randy will not get the job. So here we represent W with Randy works hard. D represents Randy is a dull boy, and J represents Randy will get the job. What are our hypotheses? We are saying Randy works hard, so W, just that. If Randy is a dull boy, then he will not get the job. So W, if W, then D. So W conditional D. And then we have if Randy is a dull boy, then he will not get the job. So okay, here. Uh, if Randy is a dull boy, so Randy is a dull boy represented by D, then Randy will get the job, negation of J. Negation of J. So now what we have to do, Randy will not get the job. We have to determine by applying laws of rules of inferences that Randy will not get the job. How do we do that? So I have done this already for you guys. So the proof here, yeah. All right. So we have W. So we have these three hypotheses, 1, 2, and 3. Okay, I'll just have it for you guys here. So 1 W, and then we have 2, and then this is the third one. So these three hypotheses we have. Okay. Okay. So we have these three hypotheses. We have to use these hypotheses to draw a conclusion that Randy will not get the job. Now we take W, and then we take these first two hypotheses, and then what we do is we apply the modus ponens. We get D, right? We name it a fourth hypothesis. We can call this a fourth hypothesis by applying the rule of inference. So for by applying we get D. We can say by applying modus ponens on 1 and 2, we get D. Okay, so we get another hypothesis for we will apply another modus ponens on the third one, and then we will get our conclusion, which is basically the negation of J, which is basically the result by applying modus ponens on 3 and 4 hypothesis. Okay, so therefore we get this conclusion. We get this conclusion that Wendy will not get the job based on the hypothesis that we concluded from the rules of inferences. Okay, any questions here? Okay, no questions. All right. Okay, so let's move on to the question number 9. 9 question says, just take a minute to read this lengthy question. Okay, all right, let's do part number A. So what we have to do is we have the collections of premises, and then we need to draw some conclusions based off these hypotheses or premises. Firstly, we have if I take the day off, it either rains or snows. Okay, so here and then we have I took Tuesday off or I took Thursday off. It was sunny on Tuesday. I did not snow on Thursday. So the conclusion that we can draw, there are a couple of conclusions for this that we can draw. Firstly, for this one, we can say I did not take Tuesday off. You guys can use different rules of inferences that you have studied in this course so far to draw these conclusions. So I'm just listed down the possibilities for different conclusions because I've already went uh, through these questions. So firstly, we have I did not take Tuesday off. The second conclusion we can draw is I took Thursday off. I took Thursday off, and we can also conclude it rained on Thursday. Okay. So, part C, I am either clever or lucky. I am not lucky. If I am lucky, then I will win the lottery. Okay. So here we can conclude that only I am clever. So we can conclude I am clever from the hypothesis that are given to us. Okay, so these again are basically the result of the rules of inferences. It is recommended that you guys make sure that you practice these rules of inferences so that you can answer the questions of these kind. Right, so let's move on to the next question. Okay, so we have to determine that what is wrong with this argument. Let h of x be x is happy given the given the premise that there exists x such that x is happy. We conclude that h Lola, therefore Lola is happy. So we have to determine what's wrong um, with this argument here. So here, the one thing that I've been stressing on the previous question so far is basically the domain, knowing the domain of the quantifiers. Since we don't know what really is the domain and if Lola is part of that domain or not. So we can say X consists of all the people in the world and Lola is one of the people in the world, then this will be perfectly fine. But because we don't know the domain, that either Lola is part of the domain or not. If Lola is part of the domain, okay, then we know that Lola is happy. But the problem is we don't know the domain. So we can say we know that someone is happy, but we cannot conclude that Lola is in the domain of X, right? So we can say maybe Lola may not be in X. So therefore, therefore make sure whenever you are working with the quantifiers, the domain is very important. You have to know what the domain is because your answer, the truth value for an argument, a propositional value, a propositional function will be based on the domain. Okay, so this is an important lesson to learn from this tutorial today. Any questions so far from exercise 1.4, 5, or 6? Okay, I'll take this as a no. And thank you very much, guys, for this tutorial. So that is pretty much everything for these 1.4, 1.5, and 1.6 tutorials. Make sure to practice a lot so that um, by the time your exam will take place, you are perfectly fine to answer any question from these exercises so far. So if you guys don't have any questions, then that will be everything, and I'll see you guys in the next tutorial.